And now let us start looking at another new concept, that is a random process. So today's module, let us start looking at random processes. So we are going to start looking at and what is a random process? A random process is a random variable is a random variable which is a function of time t. So a random process, what is a random process? If you consider a random variable which is a function of time, that is, now we are incorporating this time dimension into the random variable. So a random variable as a function of time is a random process. So random variable as a function of time, for instance x is a random variable and t is the time, that is xt is a random variable. This is what is xt? Xt is a random variable, it is a different random variable for every time instant t, that is xt is a random variable at every time instant t. This is also known as a random variable which is indexed by time, that is random variable which is indexed by time. So this time is also known as the indexing set. So this is known as a random variable, this is known as a random variable indexed by time, that is a random process. A random variable indexed by time, that is known as a random variable. And for instance, we have several random processes. A typical random process is just a random variable, some random variable that is a function of time that looks something like this. So this is a random, for instance we have here a random waveform, and on this axis over here I have time. So I have a random variable which is a function of time, that is a random process. And random process, as you can see, is very convenient to handle a large number of random phenomena, especially in wireless communication, such as random signals or even the noise process at the receiver, which is random in it. These are random variables, but at the same time these are a function of time, therefore these are random processes. So random process like this can be used to model a random signal or the random noise process or can be used to model the random noise process at the receiver. Now what about the probability density function for this random process? Random variable, remember random process is a random variable at every instant of time. So corresponding to every instant of time there is going to be a probability density function. So there will be a probability density function which is also therefore indexed by the time. So a random variable xt is characterized by the probability density function, by the PDF, by the probability density function f of x, which is the probability density function of this random variable x, indexed by time, because now a random process, because this is a function of time. So this is the probability density function of x. So what does f of x, f subscript capital X of x comma t, what does this denote? This denote the probability density function, this denotes the probability density function this denotes the probability density function of this random process x, the probability density function of the random process at the time instant t. We will now have a probability density function at every time instant t. And similarly, therefore, now we can define also this statistical parameters such as the mean, right, the mean, variance, etc., but they will also now be functions of the time t, since this is basically this random process, this random process is basically a function of time. So, one can define the statistical parameter, that is the mean of this random process, the mean or the average value of the random process is basically, what is this? This is basically your expected value, the expected value. So, we can denote this by the mean mu, which will now be a function of time, which is nothing but the expected value of this random process x of t, which is basically integral minus infinity to infinity x multiplied by the probability density function at time instant t times dx. Remember, previously we had said the mean is f x times f of x dx integrated from minus infinity to infinity, where f of x is the probability density function. However, now we have the probability density function, which additionally is a function of time. So, we are simply multiplying x by the probability density function, which is a function of time, and integrating from minus infinity to infinity. So, naturally the quantity that you obtain will be a function of time, and that is the mean, which is a function of time, that is denoted by mu x of t. So, this is our mean, and observe that this is a function of time, this is a function of time, and what we are using here, this is the PDF at, this is the probability density function at time instant, this is the probability density function at time instant t, and naturally the mean mu of x of t that you obtain is a function of time, since there is a different probability density function at every time instant t. Now, let us look at another important property of this random process, which is also known as the autocorrelation. So, we will look at another interesting property or interesting definition for this random process, which is the this is the autocorrelation, or auto also means self. So, this is basically also the correlation of the process, random process x t with itself, that is known as the autocorrelation, or basically it is also the self correlation. And how do we define that? We define the autocorrelation as, well, the autocorrelation or the correlation of the function of the random process x at two time instants t1 comma t2, that is equal to the expected value, this is basically equal to the expected value of the random process at time instant t1 times the time instant t2, that is basically the correlation. This, what is this? This is the correlation, between two times. So, what is the autocorrelation? The autocorrelation is the self correlation of the random process corresponding to two different time instants. That is, if you look at the random process x t1 at time instant t1 and x t2 at time instant t2, and we ask what is the correlation between these two, that is basically the autocorrelation, that is the average value of the product x t1 times x t2, and naturally for a general random process this is going to be a function of both the time instants, that is t1 comma t2, and therefore this is denoted by rxx of t1 comma t2, that is the expected value of x t1 comma x t1 times x t2, and this is defined as, this autocorrelation is defined as Rxx T1 comma T2 is defined as, this is defined as, let me write it down over here clearly, this is defined as minus infinity to infinity, minus infinity to infinity, x1 x2 times f of x1 x2 comma T1 T2 times dx1 dx2, and this is the correlation between two time instants dx t1 comma t2. And what is this? This is f of x1 comma x2 t1 comma t2. This is the joint probability, this is the joint probability density function for T1 comma T2. So, what are we looking at? We are looking at f of x1 comma x2 comma T1 comma T2. Remember, f of x comma t is the probability density function of this random process at time instant t. F of x1 comma x2 T1 comma T2 is the joint probability density function of this random process corresponding to time instants T1 comma T2, and we are multiplying this by x1 and x2 and integrating it over the range minus infinity to infinity over both the integrating variables, that is x1 comma x2. This is basically the autocorrelation, that is the self correlation with the random process corresponding to time instants T1 comma T2. Alright, this is the definition of the autocorrelation. This is the joint probability density function corresponding to T1 comma T2. And now we have a very special kind of a random process. This is for any general random process. Let us now consider a very special kind of random process which will come in handy when we talk about wireless and especially communication systems. So, we have a special kind of random process. A special, or you can also call this as a subclass of the general class of random processes, which we term as a wide sense wide sense stationary WSS. This is a WSS random process. So, let us now consider a specific subclass of the general class of random process, which we term as wide sense stationary or WSS random process, which is abbreviated as a WSS random process. Now, what is a wide sense stationary random process? For a wide sense stationary random process, we must have the expected value of the random process, that is the average expected value of xt is equal to mu x, which is basically as you can clearly see, this has to be a constant, that is this mu x does not, that is you can see this does not depend on the, as you can clearly see in the general definition, the mean mu x of this random process depends on the time t. That is, we said random process is a random variable for every time instant t. Therefore, naturally the mean can also be a function of the time instant t. However, if that mean is specifically for a wide sense stationary process, that mean, that average, that is expected value of this random process x of t is mu x, that is for every time instant, irrespective of the time instant t, it is a constant, it is mu of x, it does not depend on the time t, and this is basically a prerequisite. This is one of the required properties of a wide sense stationary property. And now you can see where the nomenclature stationary comes from. Stationary comes from the fact that the mean is a constant, it is not varying, it is stationary. This random process is also said to be stationary in the mean. So one can also say that this such a random process has to be is stationary this is stationary in the mean, in the sense that this random process, the mean of this random process is not changing with time. It is a constant or it is stationary with time. Now let us look at the autocorrelation for this wide sense stationary process. If we look at the autocorrelation, that is, let us consider T1 equals T, T2 equals T plus tau, where T is also, where this T is also known as this shift. T is basically this time shift, that is, we have T1 equals T, T2 equals T plus tau, that is, it is shifted by tau. And if we look at the autocorrelation between autocorrelation of the signal corresponding to these two instants, we have expected value of xt plus tau, which is equal to Rxx of t plus tau, Rxx of t comma t plus tau, and for a wide sense stationary process they should further be equal to Rxx tau, that is, it only depends on the time difference tau, that is, autocorrelation only depends on the time difference tau and not the specific time instants T1 and T2. Remember, we have T1 equals T and T2 equals T plus tau. So the time difference between them is tau, and we are saying the autocorrelation corresponding to these two instants T1 and T2 depends only on the time difference tau and not on the particular time instants T1 comma T2. Alright. So for a wide sense stationary process, Rxx autocorrelation depends only on the shift tau and not on T1 comma T2, or not on the specific time instant, or not on the specific time instant T, not on the specific time instant, not on the specific time instant T. Therefore, this is stationary. Basically, one can say this is the autocorrelation is stationary. All right. So what are we saying? For a wide sense stationary process, the autocorrelation, it has to be stationary in both the mean and it has to be stationary in the autocorrelation. So such a process which is stationary in both the mean and the autocorrelation is known as a wide sense stationary random process. All right. So basically, in this module, what have we seen? We have looked at the various properties of random process. We have looked at the definition of random process. We said random process is a random variable which is a function of time. We have defined the concept of a mean of a general random process and the autocorrelation of the general random process, and we have also seen what is the specific for a special kind of a random process, a specific subclass of random process which is a wide sense stationary process. The mean has to be constant, does not depend on the time, and the autocorrelation at time instants t and t plus tau depends only on the time shift tau and does not depend on the specific time instant t. All right. So basically, with this, let us conclude this module. We will look at other aspects in the subsequent modules. Thank you very much.